Thanks for joining us today to learn a little bit more about science at Schrödinger. To begin, let's talk a little bit about what we do as a company. Our goal is to use new molecules designed on the computer to improve human health, either by making new medicines or new materials that help make life a bit better for everyone. Let's talk about who is this Schrödinger person? Why would you name a whole company after a Nobel Award-winning physicist from Austria? Well, to begin, let's talk a little bit about where various theories of physics came from. First, we had Isaac Newton. He came along and an apple fell on his head, and he used this to develop many theories of how to explain the world around us. This is what we call the Newtonian era of physics. With Newtonian physics, space and time were absolute, and you could figure out lots of things about them. However, then a person named Albert Einstein comes along, and he has some new ideas. His discoveries of relativity helps everyone to realize that space and time can be altered by matter, and things can get kind of weird when they're really small, like subatomic particles, or when they're really large, like outer space. Shortly thereafter, Erwin Schrödinger shows up, and he has quantum theory. He says, guys, I see what you're doing here with your Newtonian physics, with your classical physics, but it's even worse than we thought. It's really hard to figure out everything absolutely. And to describe this really complicated thing, he came up with an equation, which looks kind of funky here, and this is Schrödinger's equation. It describes the movement and location of an electron. Now, this is something that we care a lot about because if you can predict where an electron is at a given point in time, you can start to predict the properties and interactions of molecules that contain electrons, which in our world is kind of just about everything. What makes this particularly hard is that Erwin Schrödinger said electrons are like particles and waves at the same time. So a particle you can imagine like a grain of sand, or a wave like a sound wave or a wave on the ocean. And Schrödinger discovered that the way you observe an electron affects how you observe it. In other words, the way you run an experiment can influence the results. And knowing where an electron is really important if you want to do exactly what our company does, which is bring molecules to life and test them on a computer. When you draw a molecule on a computer, you need to be able to have your one drawing represent all the possible shapes, properties, interactions that molecule can have, just as it would be if that molecule were in a test tube. Now, Erwin Schrödinger just blew everyone's mind here with his idea that electrons behave like waves and particles at the same time, and how you observe them impacts what you observe. So he tried to give this idea of like, well, let's imagine that we had a cat in a box. And I want to be really clear, this is a thought experiment. No cats were actually put into a box. And this is also a bit of a simplification of it. But let's imagine that we put a cat in a box, and the box is closed so we can't see the cat. Or inside the box with the cat, there's a flask of poison that will break if you open the box and kill the cat. So, as long as you leave the box closed, it's effectively like the cat is dead and alive at the same time. Because if you try and observe the cat, you will fundamentally change the nature of the cat that you see. So Schrödinger used this thought experiment to illustrate how something can be two things at once, and how the experiment that you do to observe the thing will change the nature of the thing itself. So, how does this relate to computers and making molecules on the computer? Well, as I mentioned, we're really concerned with trying to figure out where electrons are at a given point in time to make sure that we are accurately representing what are very dynamic entities, molecules, in a static way by drawing them on the computer. So to bring our molecules to life on the computer, we use some of Erwin Schrödinger's theories to be able to bring these molecules, the various properties and the various ways that they would behave if they were in a test tube, to the drawings that we have on a computer. So if we take Schrödinger's short little equation and extrapolate it out into this longer time-dependent equation here, we can start to describe motions like translation, vibration, and rotation, motions that we can imagine that electrons would have around a particle, like the nucleus and the protons of an atom. And if we start to link all these atoms together, we can start to describe the movements and interactions and properties of molecules. Now I'm going to pause here. This is kind of hard point number 1 that I want to make. Figuring out where an electron is at a given point in time is hard. And we care about it because we want to try and bring molecules to life on the computer. Now, here's hard point number 2. Designing medicines. Sometimes I might say the word drugs, just because that's how scientists often refer to medicines. But if I say drugs, I really mean medicines. Designing different medicines is really hard. If we think about a medicine that you might want to take, say for a headache, think about some of the things that you would want that medicine to do. So obviously you would want that medicine to make your headache go away. Now, it's also important that we consider what we want a medicine to not do. So if I were going to take medicine to make my headache go away, I clearly would not want that medicine to also make my toes fall off. So we need to consider what we want a medicine to do, and we want a medicine not to do. We also need to consider how we want to take the medicine. So I would much rather take a pill than to have to get a shot. I would also like to be able to take that pill maybe once a day instead of once an hour. And I would like that pill to be, probably small, easy to swallow, and ideally not taste really bad. So if we think about all the different properties that we need a medicine to have, this can be a lot. And often what we have is a scenario where we have one molecule, let's call it molecule 1, and it ticks almost every box that we need it to tick in terms of the properties that we want it to have, except for one. And in trying to make that property fall into the range that we need it to fall into, we go back and iterate and design molecule number 2 to make that property fall into line that we need it to be, and we accidentally knock 2 other properties out of whack. And then so we go back to the drawing board, we design molecule number 3, and in trying to fix the other 2 properties that we accidentally knocked out of whack when we tried to fix the first property, we accidentally knocked some more properties out of whack. And this can go on for quite some time because it's really difficult to find one molecule that satisfies all those properties. And what makes this particularly tricky is that these properties may or may not have intuitive or logical relationships between them. It may not necessarily be apparent to scientists that in trying to optimize property number 8, we are putting properties number 6 and 9 at risk. And so this process is something that we call lead optimization. And when we look at the whole overview of how drugs are discovered, what we would call the drug discovery pipeline, or some people refer to it as bench to bedside, we can see that the lead optimization stage, trying to get all those boxes to be green or all the properties to be satisfied by one molecule, is the most expensive part of the whole process. We often hear about how expensive clinical trials are. That's the part down here in blue, and they are quite expensive. But if we look at the whole process, the lead optimization part is typically the most expensive part of this process. And if you look a bit more closely, you might see that these numbers come from a reference that's pretty old. And most people would say nowadays it costs close to $2.5 billion to get a single drug to the market, to be available to people who need to take it. Now, if you were to guess how long this process might take, what do you think? If you were thinking somewhere along the line of 10 to 15 years, then you would be right. So this is a really bad situation. If you were sick and you came to me and said, Jenny, I'm sick, I don't have a good medicine that I can take, can you help me out? I'd say, yeah, sure, we can do this. I'm just going to need about $2.5 billion and come back to me in like 10 to 15 years, and then we'll see what we can do. So this is clearly not something that works. We need to figure out a way to dramatically cut the cost and time associated with developing new medicines, because people are sick today. They can't wait 10 years or 15 years, and $2.5 billion is a whole lot of money. Another way we can think about this is we can look at how many medicines have we been able to make over time with $1 billion. And starting in the 1950s, that was a pretty good amount of medicines. But then over time, we've really lost bang for our buck here. And you can see somewhere around the 2000 point, we crossed over the threshold to making fewer than one medicine per $1 billion US spent. And sometimes this is for very good reasons. So the FDA, or the Food and Drug Administration, is the entity that makes sure that the things that we put into our bodies are safe, and making sure that the regulations are very, very stringent to help keep people safe. So that's clearly really important. But what we're hoping to do now, that computers have gotten so fast and so prolific, calculations that used to take days, weeks, or even months can now be done in minutes or maybe hours or seconds in some cases. Now calculations in this digital era can be done in a way to help scientists move their drug discovery projects forward at a much faster rate than we previously could. So what we're hoping to do here is reverse this trend and start bringing this line back up and make more medicines that cost less money and come out more quickly. So if I were to ask you guys, how many medicines do you think we could make? I want you to imagine, if we were to look at all the molecules that make medicines and try and figure out, okay, what are all the possible combinations of atoms that are commonly used to make medicines that fit the characteristics of medicines that we commonly take today? If you were to imagine how many molecules that could be, how many do you think that would be? Now, the estimates vary a little bit, but most people put themselves somewhere in the realm of 10 to the 63 possible molecules. That's 10 with 63 zeros behind it. This is something we refer to as drug-like chemical space, which is a fancy way of saying all the possible molecules that look like they could be drugs. There are scientists out there that think there aren't enough carbon atoms in the entire universe to make all of these 10 to the 63 possible compounds. So all this to say, it would be impossible to just make and test everything. So we're going to have to be a bit more clever than that. But there's a lot of possibility out there, and being able to evaluate all that possibility is something that could help scientists make better decisions. Now, we clearly can't make all of these 10 to the 63 molecules and test them, so what's something else we can do? Well, computers are really, really good at performing complex calculations over and over again very quickly. So this is a picture here of about 19 million of those possible 10 to the 63 molecules. And each dot here represents a molecule. And the closer these dots are, the more similar we would consider these molecules to be. So the further away these dots are, the more different they will be. So let's say you're in a lab testing molecules in this blue area here. But it turns out the best molecule for what you're trying to work on is over here in this red area. There are just too many molecules in between to be able to test everything by hand. And statistically, your chances of just picking various points out of these 19 million possibilities here is pretty low that you'll happen to land on the right one. So what we can do with computers is start by evaluating a much larger swath of this chemical space, a much larger amount of possibility than a person or a whole team or even a team of robots could evaluate. Computers can do this by building molecules virtually, bringing them to life using some of Schrödinger's equations, and testing them using the mathematics that underpins the observations that we would see if we had these molecules and were testing them in a lab. So being able to test a much larger area of chemical space is something that we are hoping that computers can help scientists do to make better drugs and to make them more quickly with less money. So, how can we bring these molecules to life? Scientists will often start by drawing a structure of a molecule. So this is a way to represent a molecule, similar to how you might read music and you would know that a dot that is open is a whole note, a dot that is filled in with a little flag is a quarter note. Scientists, in particular chemists, might look at these structures and know what they represent. Each corner represents a carbon, a single line is a single bond, a double line is a double bond, and so on and so forth. So we take these structural representations, we mix it in with the fancy math that is brought to us by Erwin Schrödinger and others, and we run it through a lot of computers. And what we end up with at the end is a physics-based simulation of molecules. So this is a simulation of molecules that has gone right back to our best interpretations of the physics, which is the mathematics that underpins how molecules and atoms are going to want to behave and interact with each other. Now, if we think about the different ways that molecules might want to move on a computer, or in real life, if we had two atoms bonded together like I and J here, we can imagine them moving back and forth, in and out. If we had three atoms bonded together, they might want to bend at a harmonic angle. Or we might have a dihedral angle, where it's kind of like this molecule or this atom K is being swung around in a circle. We also have ways that atoms can interact through space, such as electrostatic or van der Waals interactions. And all these interactions can be described with a lot of math. And I'm pretty thankful that I don't have to solve all this math for every molecule that I'm interested in by hand. So again, this is where those computers that can rapidly perform complex calculations come in. So let's talk a little bit about how we might end up with a 3D model of various compounds that we're interested in studying. So a lot of times when it comes to designing medicines, scientists will look at a particular protein that is involved in the disease that they are studying. Proteins are like the machines of your body. They perform various tasks, and sometimes if these things go wrong, these tasks or the protein itself, something can get messed up, and this can lead to a disease state. So you can imagine a protein that controls cell growth. If it gets stuck in the on position and cells grow unchecked, this can lead to cancer. Likewise, we could have the inverse, where a protein that controls cell death might get stuck in the off position. And again, that can lead to uncontrolled cell growth, which can be cancer. So to be able to design medicines for these proteins to help fix whatever it is that's not working about them, it's really helpful to have a 3D shape of these proteins. 3D shape often controls these processes in our body. So you can think about it in terms of a lock and a key, but that's kind of only a good starting point because these proteins are, like our molecules, dynamic and always moving around. So let's talk a little bit about how we would get a 3D structure of a protein. We would get a protein to crystallize, so thinking about crystals and how, say, like sugar crystals might form in a solution, we can get a very talented scientist to make a protein crystallize. If we get a protein crystal that is of sufficient quality and size, you can hit it with high-powered X-rays. These X-rays will bounce off the atoms in the protein crystal, something known as diffraction. And the way that these X-rays bounce off the atoms will create a diffraction pattern. Once again, using fancy math, we can figure out, based on where these X-rays have diffracted, where electrons from the protein were in space. This would give us an electron density map that we could put back onto the known amino acid sequence of a protein and end up with a 3D atomic model of that protein. So again, being able to see a protein in 3D. What's the shape like in 3D space? This is pretty amazing. This is like starting from an architect's design for a house, the known amino acid sequence of a protein, and then being able to look at the house after it is completely built. That's the 3D atomic model. What can make this really tricky, though, is that proteins, like molecules, are always moving. So even if we have a drawing of them holding still, or a 3D structure of them in one shape, proteins are always moving around and making different shapes in our body. So if we think back to that starting point of the lock and the key, this would be like trying to design a key to fit a lock that's wiggling around constantly. Luckily, most proteins, like this one, have a somewhat predictable shape in what we would call a binding pocket. So this would be a part of the protein where we could get a small molecule, such as a medicine, to bind and be able to modulate what this protein does in our body. But not all proteins have a binding pocket. Some proteins change shape so drastically, kind of like what we might see at the bottom left of this molecule, that it's really hard to figure out what kind of quote-unquote key could fit there. So all of this to say, designing medicines is a really hard thing to do. We need to be creative to try and tackle this problem. Not only are there too many molecule options out there to test them all, but it takes too much time and too much money to try and make one medicine. So here's where we're going to mix hard point number 1, where an electron is at a certain point in time, with hard point number 2, trying to design a molecule to be a medicine. And this is what we do with our software at Schrödinger. Using these 3D atomic models of both proteins or small molecules, or in the case of materials, sometimes very, very large, complex atomic systems, we try and design these virtual molecules on the computer, bring them to life using Schrödinger's equations, and test them in a very similar way that you might test molecules in an actual lab. So depending on the particular kind of research you want to do, each scientific task would have its own questions and own tools and own particular hurdles that they need to overcome. My background is in chemistry, and so I most often deal with small molecules, what we might typically design as medicines for various diseases. However, with Schrödinger software, we are able to tackle all of these problems. So we can look at biologics, so things like vaccines or antibiotics. We can look at small molecules to be medicines. This would be something more familiar like aspirin or ibuprofen. We can also use these same theories to design different materials, such as metals that are going to be more durable but less heavy to make new planes out of. Now, this is really great that we can do all this on the computer, but it begs the question, does it actually work? And I'm really happy to tell you we have more and more cases that we can point to say, yes, it does. One particular research project that we are very proud of is looking at a liver disease where a particular protein called Acetyl-CoA carboxylase, or ACC, somehow gets messed up. And we needed a better medicine to be able to fix this particular liver disease. Now, there was a medicine out there, but it wasn't particularly great. And when we tried to look at the structure of both the medicine and the protein, the ACC, we weren't able to see really a clear path forward for how we could design a better medicine. So we were able to use our software to perform a calculation that would look at the waters that surround this particular protein in the binding pocket and see if we could use this information to design a better medicine. In this case, we needed a medicine that would be able to bind more tightly to this protein, so a key that was a better fit for this lock. And we were able to see, well, if we built a molecule that had this particular 3D shape, we would be able to kick out what we would call some unhappy waters, some waters that were kind of stuck in this binding pocket. And this would allow us to build a molecule that would want to bind more tightly to this particular protein. The important part of this all is that a time frame that usually takes about 6 years was able to be compressed into about 16 months. So we're able to start with designing new compounds using a technique we call virtually screening compounds, to be able to get all the way from design to getting a compound into those clinical trials in 16 months. So this was something we're really happy to see. It worked. It cut down the time, which means it also cut down the money to design this medicine. And we're really excited to say that it is still progressing through clinical trials at a good rate, and hopefully soon there'll be a new medicine available to people who have this particular kind of liver disease. Now, the next question that springs to mind for me is, cool, I really like this, it works, who all gets to use it? And I would say everyone gets to use it. This software is easy enough that we regularly bring our own daughters and sons into work for a Take Your Kids to Work Day, and they are able to use this software. And you too can also use this software. We have a free version of our software that you can download for academic use and to start to design and play around with some molecules. See how they are in 3D. Now, I think that this is an exciting point because this is not where the story ends. We don't have this solved. We still have a lot of questions and a lot of research problems to tackle here. And so we need everyone. We need people who are really interested in chemistry, people who have a desire to find new molecules to solve problems, both in biology or material science. So there's lots of things out there that still could use a hand. We need people who know some biology and love to dig into the human body and figure out how does it work and what goes wrong in particular diseases. We need people who are really interested in physics to keep pushing the boundary of what we know about physics. Erwin Schrödinger was right. It gets really hard when things are very, very small. Figuring out where that electron is in space is still pretty difficult. So we also need people who love math to be able to work with, again, our best known approximations of these really, really complex mathematical operations to be able to figure out ways that we can balance scientific accuracy with computational speed. We also need people who know how to design medicines. So again, I would rather swallow a pill than take a shot when it comes to taking medicine. Being able to design a medicine to be easy to take and something that is available for a wide amount of people doesn't happen on its own. We need people who know these particular skills as well. So I am really excited for everybody to learn more about how computers can design and test molecules to make new medicines and new materials. And I hope that you have taken away some new ideas for how we might be able to go about that. So for all the aspiring chemists, physicists, mathematicians, biologists, doctors, computer engineers, chemical engineers, keep an eye on Schrödinger. We would love to have you join us in a few years. Thanks again for taking some time to listen to this talk, and feel free to get in touch with our team at education@schrodinger.com with any questions you might have. Take care, and good luck with your science.